Hi, my name is Walker Daniel, and today I'll be presenting Lab 1, Constant Velocity. The purpose of this lab was to compare the observed velocity of an object at a constant speed to the predicted velocity found using code. This experiment, the object that I used was a small metal ball, and this will be, of course, the system, and all forces acting on this ball will be the work. The observed velocity was tracked using a software called Tracker, and the predicted velocity was computed using GlowScript. And this lab helps demonstrate Newton's second law. Newton's second law states that the net force is equal to the change of momentum divided by the change of time, and we can manipulate the formula to create a velocity update formula. As you can see here, we got F net, and we bring momentum to the other side, change momentum to mv mass and volume, and then of course divide everything by mass, and then you get your velocity update formula. And this will help us show the final velocity. Based on this equation, we can tell that with no change in net force, so if net force equals 0, there will be no change in velocity, and the ball will be moving at a constant speed. There should be no change of velocity. And after using this equation with our observations, we can tell that there has to be some external forces because the velocity changed. The procedure I followed goes as followed. First, I recorded a brief video of the metal ball rolling across a flat surface at a constant speed. And then I imported this video into the tracker program and marked the position of the ball at each frame. Then I created a string of code that calculated the predicted movement of the ball using GlowScript. And then finally, I compared the movement versus time graph generated by Tracker and GlowScript. And here's the video I used for this lab. And here are my observation results. My initial time was 0. My final time was 0.034 seconds. My initial position was this pretty small number here in meters. And then my final position was this slightly bigger, but still small number right in meters here. The mass of the ball, although it does not affect our calculations, with 56.2 grams. And then finally, the net force on the ball was predicted to be 0. And plugging all this in first to our velocity formula, we get 0.336 meters per second. And then we use this as our initial velocity and plug it in to our velocity update formula. And we get the same number because plugging our net force of 0 into the equation just yields the same velocity. And then here are my predicted results. I used the same data from the observed, and we can see that mass goes here. This is where our vectors are for position and velocity. And then finally, this is where all the math happens. And these are our graphs that we got. On our left is the observed graph, and we can see it curves slightly, showing it's slowing down a little bit. And our predicted graph is straight linear. And this shows us that something went wrong. And here are our errors, or possible errors. First are some outside forces. This could be my initial push off the ball could have generated some acceleration that was not calculated for. And then also some friction from the table and the bar it was rolled against. Also, there could have been some tracking issues. I had a pretty small object, and it was hard to tell exactly where the center of mass was because it was on a reflective surface. And then finally, there could have been some rounding errors because I was using some pretty small numbers for my position, and that could have affected my calculations. And this leaves us with some additional questions. What if the original orientation of the axes were flipped from x positive to x negative? And this would only affect the slope of the graph, which would make it negative. And that is because our axes are relative, so it's kind of how we perceive them, and it affects none of the physics whatsoever. And also, is it possible for you to say how many pushes and pulls are being added together to give a net 0 force in the cases that you observed? And we could tell that it was not a net 0. As we discussed in our possible errors, there are some factors that could have affected this, which are friction and the initial push. But also there was a net 0 on our y-axis, which was caused by gravity and normal force, so nothing changed there. All right, that's all I have. Thank you so much.